Beyond Imagination CNC 1310 Overkill Edition. Oh no, I've done it again. What a sinful man I am. I've probably made so many people sad again. What should I do?
Well, freak. Long time no see. What's bothering you this time? Did you mess up again?
Hey, Angel. Yeah, it's been a while. I haven't uploaded any videos to YouTube recently, but finally, I managed to finish a new one. But you know, I've been reflecting a lot.
I noticed you weren't uploading anything lately. I honestly thought you quit YouTube. I figured all your failures finally got to you, but you don't have to worry about that. Everyone enjoys watching your failures, so cheer up. And what kind of funny mistake did you make this time?
What are you talking about? I would never make such mistakes. The thing I'm sad about is this. I created something so outrageous, so unimaginable, that I might have made CNC modders all over the world realize they can never catch up to me anymore. And when I think about how sad that must make them, I can't help but feel guilty.
Yeah, no. I'm pretty sure you don't need to worry about that.
But, Angel, I wonder if you'll still be saying that after watching this video to the end. This time, the modification I did was on that little red home router, the CNC1310. I've modded it a few times before, but this time, I went way beyond that. Actually, I think I might have gone a bit too far. I mean it. This modification is so far beyond imagination. I'm almost scared of myself.
Oh, stop mumbling and just explain already.
Well, I guess I have no choice. Since Angel insisted on seeing my brilliantly modified masterpiece, I'll grant your wish.
What? Hey, the music's a bit loud, isn't it? Think about the neighbors. The production's a bit overkill.
Sorry. I got a bit carried away as it's been a while since my last video. Here it is, the machine I modified. Pretty different from the original, isn't it?
Yeah, the original was small and kind of cute, but this one has some serious weight to it, especially the table and the motor. Those are absurdly huge.
That's a pretty large table, isn't it? It's actually one of the key points of this entire modification. And I installed the biggest motor I could reasonably fit, so it can cut steel with plenty of headroom.
You were cutting steel in your last mod too, but I wouldn't say you had much margin for that. And the noise was awful. I kept thinking you needed some kind of noise reduction setup. I'm an angel. You know, I'm sensitive.
Don't worry. I'm always grateful to all the beautiful angels, other than you, who blessed me with talent. So, to make sure the real angels out there would like this machine, I made it quiet. Noise happens when a machine lacks rigidity and starts vibrating. So this time, the X and Y axes were upgraded from linear shafts to linear guides. The column's cross rail was rebuilt with epoxy granite for higher stiffness, and even the spindle, I made it myself to ensure the rigidity I needed.
The spindle has a cover on it, so I can't see the inside. What's going on in there?
Well, inside here, I can't just show it for free. There might be some cutting-edge technology assembled in a clean room. You never know.
Wow. I've heard industrial spindles are built in clean rooms because even tiny dust particles can affect performance. Is your spindle made that way too?
Well, I don't exactly have an industrial clean room, so I just wiped my hands really well before assembling it.
So basically, you just put it together in true DIY style.
Let's not get stuck on the little details. Let's move on. One of the biggest upgrades this time was the CNC control system. Originally, this machine ran on GRBL, which is a very simple CNC controller. But now, I've upgraded it to LinuxCNC, the most powerful free CNC control software available. Since I'm already building a 5-axis CNC machine, and I previously built a CNC lathe, I could reuse a lot of the same units, which made the setup surprisingly easy.
LinuxCNC really is the best choice.
The original machine didn't have any home switches, so of course I added them. Alright, let's try homing it.
It looks like the table is just stretching out endlessly. What's happening?
This machine uses the table as the base design. The original frame actually moves underneath the table. Because of that, the y-axis travel increased quite a bit.
But still, isn't the table way too big? You didn't have to make it that huge, did you?
The table is 400 millimeters long and 200 millimeters wide. The travel is about 150 by 150 millimeters. So yeah, compared to the travel, the table looks oversized, but having extra table area outside the travel is a huge advantage for clamping workpieces. And thanks to this design, the lead screw is completely hidden under the table, so it doesn't get buried in chips anymore. In the original machine, the lead screw was totally exposed. It was a disaster.
I see. Yeah, that really was terrible.
Alright, let's test the rigidity of the machine. We'll use a dial indicator to see how much it deflects when I apply force.
Just pushing it with your hand makes it move about 0.1 millimeters.
That's probably because the Z-axis is still using the original linear shafts. I might replace the Z-axis with linear guides eventually.
Why don't you just replace it?
Yeah, maybe. You're probably getting excited to see a test cut by now. Let's start with aluminum.
It seems to be cutting without any issues, but the spindle speed looks pretty slow. Shouldn't you crank up the RPM a bit more?
The motor's maximum speed is 3000 RPM, but because of the pulley setup, the actual top speed is around 1300 RPM. Most home CNC machines lack rigidity, so people usually compensate by running them at high RPM, which makes them incredibly loud. But I know that weakness very well, so I increase the rigidity as much as possible and optimize the machine for low speed, high torque machining.
Well, it is quiet. It's nothing like the noise it made before the modification. But this sound is a little strange. It almost feels like it's echoing. Is that just a characteristic of low RPM cutting?
Good observation. High RPM and low RPM cutting do make different sounds, but this weird noise is caused by something much more technical.
What is it? Tell me.
I love using the best tools, so I use a very high-end camera for recording. But the camera was too good, and its noise-canceling system kicked in, so it mistook the beautiful machining sound of my machine for background noise.
So basically, you just messed up your mic settings, right?
Anyway, there's still a lot I want to show, so let's fast forward a bit.
Other than the machining sound, everything seems to be going smoothly. And yeah, the machine really does look rigid.
Of course. Everything I do is absolutely perfect.
Oh, sewer.
Angel, I bet you're getting curious about what CAM software I use to create my machining programs, right?
No, Not at all. The only thing I'm curious about is why the machining sound got weird, since you messed up your mic settings.
Alright. Since you clearly want to know, I'll tell you something special. I actually don't use any CAM software. I use NGCGUI, an extension inside LinuxCNC. With this feature, you just type in the numbers you need in a GUI, and it automatically generates the machining program. Just fill out the form on this screen, and the G-code is done.
Oh, I see. Your explanations are always so confusing that now I am curious. But if I ask you, it'll probably become even more confusing, so I'll just ask Ultimate instead.
Long time no see, Angel. Thanks for calling me. What's going on?
Nice to see you again, Ultimate. So, Freak has been talking about some LinuxCNC extension, but honestly, I don't really get it. I mean, his face and brain being questionable is nothing new, but if his explanation is bad, the viewers will suffer. So I want you to explain it properly.
Hey, wait a second. Didn't you just say something weird? Besides, you're the one who tuned the ultimate GPT I developed in such a strange way. That's probably why the answers are so biased now. Can you reset her already?
That's not true at all. Thanks to your tuning, Angel. My answers are far more accurate than before. By the way, don't you look even more beautiful than last time? You're shining so brightly it's almost blinding.
Oh my. You really are high performance. The recent progress in AI is incredible. Alright. Ultimate, please make up for Freak's shortcomings.
Alright, Angel, let me explain this in a beginner-friendly way. NGCGUI is a built-in feature of LinuxCNC that helps you create machining programs. Normally, you would use a CAM program and go through many complicated steps to generate G-code. But NGCGUI works differently. You simply enter numbers into a graphical interface. Things like position, depth, or number of passes. And it automatically generates the machining program for you. What makes NGCGUI really special is how customizable it is. Each machining operation is separated into small subroutines. You can add your own routines or combine existing ones to create new machining workflows. That means NGCGUI is easy for beginners to use, yet powerful enough for advanced users. You don't need a CAM program to build your own machining environment. That's the true strength of NGCGUI. Now, doesn't that sound clearer than Freak's explanation?
What are you talking about? You're just an AI. All you can do is talk. I'm a genius engineer. Engineers don't need to explain things. All that matters is the result. Besides, I wrote this NGCGUI subroutine myself. Now watch closely. I'm going to do a slot cut. This is what a real engineer's work looks like. Why?
That was a slot cut. It looks pretty different from the LinuxCNC simulation.
This is, well, basically, it was totally planned.
Since Freak's explanation is confusing, I'll explain. What you just saw was a slot cutting program executed using NGCGUI. This kind of behavior is usually caused by either a programming error or an incorrect tool setup. In general, this phenomenon is called a crash. Or, in simpler terms, an idiot doing something idiotic.
Oh no, I failed. I never make mistakes like this. I rushed the machining. I'm done. I don't think I can recover from this. My heart, it's broken, just like this end mill.
Did I go a little too far, Angel?
It's fine. This will fix him instantly.
Hey, someone stop him. This is bad. If he drinks that much, Freak is going to break.
It's fine. He was already broken.
Hey, everyone. Earlier, something was missing, but now I'm fine. Right now, I feel like I'm driving a car on the highway with a stuck accelerator. I'm in perfect shape. Sorry about earlier. You had to listen to Ultimate's slightly incorrect explanation. Now, let me explain why I intentionally crashed the end mill this time.
Is he okay?
Maybe.
In most home CNC routers, each axis is driven by a stepper motor. Stepper motors are great because they're very easy to control, but they also have a drawback. When too much force is applied, they can lose steps, and you no longer know the correct position. Unlike servo motors, standard stepper motors don't have encoders, so even if the position shifts, the machine has no way of detecting it. To solve this, every stepper motor on this machine is equipped with an external encoder, and to demonstrate that, I intentionally crashed the machine.
Who's going to believe that Freak did that on purpose?
No one would believe that.
Now let's take another close look at what happened during the crash. When the end mill hit the material, a large amount of resistance was applied, and the machine briefly stopped. Then, once the end mill broke, the resistance disappeared, and the axis quickly moved to the position it was originally commanded to reach. This kind of behavior happens because the machine is equipped with encoders, which continuously monitor and correct the actual motor position. This was a perfectly calculated, easy to understand explanation. If you thought this demonstration was amazing, I'd really appreciate it if you helped cover the cost of the end mill with a super thanks.
Angel, I'm starting to feel embarrassed to be on this channel.
There's a limit to how stupid you can be.
Alright, let's try a slot cut. It's cutting with plenty of margin. We could probably push the cutting parameters a bit more. This part will be used as a stopper to secure workpieces on the table. The machining went smoothly without any issues. Next, let's try machining steel. You don't often see videos where a modified home CNC router is used to cut steel. When machining starts, the tool first cuts through the hard mill scale on the surface, so the cutting sound gets a bit louder. But once it cuts past that layer, the machining becomes stable and there's plenty of margin. We could probably push the cutting conditions a little more.
What's mill scale?
Mill scale is an oxide layer that forms on the surface of steel when it's hot rolled at high temperatures. It looks like just black steel, but it's actually harder and more difficult to cut than the material underneath. That's why the sound gets louder right at the start of machining. Once the mill scale is removed, the tool reaches normal steel, and the cutting becomes stable.
Yeah, that's basically it. Not bad for an AI.
The machining looks smooth. The audio sounds natural now too, so you finally fixed your mic settings. Nice. But even though it's hard to tell just from the video, isn't the machine vibration a bit too strong?
I think the machine has enough rigidity to handle machining steel. I've properly fixed the mic settings, so now you can hear the real cutting sound. And yeah, you might be right. The vibration does feel a bit excessive. Judging by the vibration frequency, it seems to be related to the spindle speed. Let's investigate that. If the vibration changes with the spindle speed, then the most likely cause is that the pulley mounted on the spindle isn't properly centered. Let's take a closer look. This is the highest point.
So you're measuring the highest point of the timing belt pulley.
Yes. And this is the lowest point. The runout is about 0.35 millimeters. That's quite a lot. So let's make this adjustable. First, I'll take it apart and modify the pulley so it can be pushed from 4 directions using set screws. Then, while tightening the screws, I'll adjust the center.
So this is what the inside of the spindle looks like.
Oh, wait. I was planning to keep the spindle's internal structure a secret, and now you've seen it.
Then explain how you built it.
Nope. When you want a machine that can cut steel, there are many things you need to improve the rigidity of the X, Y, and Z axes, and backlash in the lead screws, for example. But especially with modified home CNC machines, people tend to underestimate spindle rigidity. This time, the spindle rigidity is perfect. I can't just give that away for free.
Ultimate, please.
Alright, Angel. I'll explain what's inside Freak's spindle in a beginner-friendly way. First, the motor. This is a NEMA 23 servo motor with a maximum speed of 3000 revolutions per minute. It can be driven like a stepper motor, but because it uses an encoder for feedback, both position and rotation are much more stable. It also produces good torque at low speeds. Next, the pulley and timing belt. Instead of a direct coupling, the motor drives the spindle through a belt system. The maximum spindle speed is reduced to about 1,300 revolutions per minute. By changing the pulley ratio, the speed is lowered and torque is increased, and vibration from the motor side is partially isolated. However, if the pulley is off-center, you'll get vibration synchronized with the spindle speed. So proper alignment is very important. Now, the most critical part, the bearings. A spindle doesn't just spin during cutting, the end mill experiences side loads. That's why the shaft must be firmly supported by bearings to reduce deflection and play. If the bearing layout or fixation is poor, steel cutting will quickly lead to vibration and chatter. That's why this spindle uses KOYO32004 tapered roller bearings. They're not suitable for very high speeds, but they provide excellent rigidity. Finally, the spindle shaft. The tool interface is ER11, but the shank section has a 20 mm diameter, and that thicker section is what the bearings support. So even with an ER11 collet at the nose, the large supported shaft diameter greatly improves rigidity. It's not as simple as saying ER11 is weak. What really matters is where the shaft is thick and how it's supported. You'll hardly ever see a home CNC machine using a 20 mm diameter spindle shaft. In short, this spindle isn't designed to rely on high RPM to compensate. It's designed with belt reduction and a solid support structure, so it can cut with torque and stability at low speeds. See, freak? That's hardly a secret.
While Ultimate was giving that long explanation, I finished adjusting the pulley. Right now, the runout is about 0.15 millimeters. It's not exactly high precision, but let's do a test cut for now. My spindle secrets have been completely exposed, but assembling and tuning a spindle like this, that's something even an A I can't do. Not bad.
Not bad.
Not bad.
Hey, this has been bugging me for a while. You're using coolant while machining, right? Honestly, isn't that kind of a hassle? Isn't there a better way?
Yeah, you're right. I'm going to install a coolant pump eventually anyway, so I might as well do it now. Actually, the main project of this YouTube channel isn't this machine upgrade. The real main project is a 5-axis CNC machine. That build is already pretty far along, and it already has a coolant pump installed. So for now, I'll temporarily transplant that pump and use it here. This is a peristaltic pump. It moves liquid by squeezing a tube, so the structure is simple and easy to work with. It's perfect for supplying a small amount of coolant. Coolant actually has 3 main roles. First, it reduces heat during machining. Second, it works as lubrication. And third, it helps remove chips. If heat reduction and lubrication are the main goals, only a very small amount of coolant is enough. With this flow rate, chip removal isn't really possible, but that's acceptable.
Why? Why not just use a lot of coolant and wash the chips away too?
If you use a large amount of coolant, things like coolant recovery and waterproofing become a real headache. So I decided to use the minimum amount of coolant, just enough that most of it evaporates from the cutting heat. That way, I don't need any additional equipment. Yeah, looks like I still have to remove the chips manually.
See, doesn't this just prove that you should automate it?
Because the machine is rigid, the chips are actually pretty thick. I also noticed that the spindle shaft was heating up slightly during machining, so I added a cooling fan to keep it under control.
That's cool.
One common problem with home CNC machines is noise. But this machine measures about 60 decibels at roughly 1 meter away. That's about as loud as someone speaking in a slightly raised voice. Honestly, it's quieter than I expected.
There's a lot of chips building up. If you can't flush them away with coolant, why not add a vacuum or something?
Yeah, we definitely need to deal with that. If possible, I want to solve it in a way no one else would even think of. This steel plate is 9 millimeters thick, and when I try to cut the full 9 millimeters depth with a 3 millimeters end mill, the chips get packed in, and the tool ends up chipping or breaking.
The cutting edge is completely gone. I wonder when this happened.
I'm not exactly sure, but something definitely felt off partway through. Once this part is finished, let's try a 4 millimeter end mill. Perfect. As you can see, what I was machining here is a clamp bar for this machine. One isn't enough, so I'm going to make another one. With this machine, a 4 millimeter end mill should be no problem. The risk of breaking the tool should be pretty low.
And since the machining program is already done, this one's easy. This machine has more than enough torque to handle a 4 millimeter end mill.
Of course it does. Who do you think built this machine?
You know, that attitude is really annoying.
I get it. But there's nothing you can do about it, Angel. Freak has a naturally poor memory, so he forgets his past failures almost instantly. And on top of that, thanks to drinking too much, his memories tend to get selectively distorted.
Your explanations are always perfect.
Look at this. By modifying a home CNC machine, I managed to machine 9mm steel like this. Don't you think my work is perfect?
The surface finish isn't that great, and I don't think you can really do drilling, can you?
Of course I can. I'll use a 2.5mm drill. It's a common size for M3 tab drill holes.
Because the Z-axis travel is short, once you mount the drill, there's only a few millimeters of clearance left above the table. That means you can really only machine thin sheet metal, right? Wouldn't it make more sense to buy a shorter drill?
What are you talking about? Unlike you, I obviously planned for that from the design stage. This machine is designed so that the spindle unit position can be easily adjusted.
Damn, that really gets on my nerves.
Being able to adjust the spindle unit height is impressive, but the wires aren't long enough. If you move the y-axis forward like this, the wiring will run out of slack. Maybe you should have planned the wire length a bit more carefully.
Shut up.
Nice one. Ultimate.
Drilling works without any issues. Perfect. That's it for today's video. Did you enjoy it? This machine is actually built to support the main project of this channel, the 5-axis DIY CNC machine. So stay tuned for the main project. I think you'll be seeing this machine doing a lot of work there. If you are interested in this project, I suggest you subscribe to my channel so you don't miss any videos. If you empathize with my project, why don't you become a member and support this channel? There are a few benefits, but as long as you are a member, your name will appear at the end of the videos as a patron. In other words, you can be a part of this project. So, please look forward to the next video.